Hello, good morning, friends. So, today we are going to talk once again on circular motion. It's a continuation of my old series on circular motion. This will meet the second lecture. Okay, so in the last class we had spoken about what do you mean by uniform circular motion. First of all, we spoke about what is circular motion, uniform circular motion. Then what are the different quantities that we use in uniform circular motion. Namely, we have seen what is speed, what is linear speed, what is angular speed, angular velocity, and so on. Okay, and then we also explored some other quantities like time period and frequency. And today what we'll do is we'll look at non-uniform circular motion. And in the last class, I had also introduced you about this particular slide about what is the difference between a uniform and a non-uniform circular motion. In a non-uniform circular motion, as you observe, the speed, the tangential speed does not remain a constant or it keeps on varying. Say, for example, if I keep a particle here, and the smaller arrows that I have shown over here, so at every place you see, the speed of the particle nearby to the center here is smaller, and here it is a bit larger, and here it is much more larger, and here at the circumference it is very high, right? So therefore, if you are standing on a rotating disk, for example, if you are standing on a rotating disk nearby to the center, then you will definitely not experience not much of speed. Okay, you will not be thrown away. But as you move away from here, you will experience a larger speed. You feel that you are moving with a much faster speed. Okay, so therefore, say non-uniform circular motion is one which denotes a change in the speed of a particle moving along a circular path. Generally, when we talk about circular path, we have assumed that the speed is constant, but here this speed is also varying, right? So which means that earlier you had only one acceleration. What was the acceleration? The acceleration was only due to the radius, along the radius, which is nothing but your centripetal acceleration. Now you observe that there is one more acceleration coming into, which is because of the change in the speed. So that's what, so the speed at which the particle moves across here, this is known as a tangential velocity. This arises due to two possibilities. One is the radius of the circle is constant or the centripetal force is constant. So what do we mean by radius of the circle is constant? Which means the speed can change while the radius remains a constant. This can happen. Or you can also observe that the centripetal force is constant. What do you mean by centripetal force? Centripetal force, as we know already, it is nothing but mv square by r, right? Where v is the speed of the particle. So this mv square by r is a constant. So if mv square by r is a constant and we say that v is also varying, what does it mean? It means that as v varies, r also varies, right? As r also varies. In other words, it is no more in a circular path, but instead it's a spiral path. It's in a spiral path. An example of this is nothing but take a stone and then put it to a rubber band and now start swinging it. Now, as you start rotating it, what happens is the stone starts moving rapidly away. It describes a smaller circle initially, and then it keeps on describing a much larger and larger circle, right? So this is what happens in the second case. So in these two cases, you can observe that non-uniform circular motion exists. Now, in the first case, as you see, when the radius of the circle is constant, which means the speed is changing, or mv square by r is changing, which means the centripetal force is variable here. The centripetal force is variable in the first one, and in the second case, the centripetal force is a constant. Right. In a non-uniform circular motion, the angular velocity is not a constant. So definitely, angular velocity is not a constant. Let us look at some examples. Now, as for example, you see a person has dropped a particle from here. Now, as it drops over here, okay, the particle comes all the way along and it executes a circle over here. If you look into it, as the particle keeps on coming down, the speed is increasing larger and larger. But when it goes away from here on the top, because of the gravity, it is slowing down. It is slowing down. And when it reaches here, it is still lesser. Don't worry about what is given here. It is for some other problem. We will see later on. Okay, so therefore, so it changes over here. So thus, greater the speed, greater the radial acceleration. As we know, so we are looking at the first part where the radius is a constant. Radius of circle is a constant here. So when the speed is larger, the centripetal acceleration is larger. A particle moving at higher speeds needs larger radial forces to change its directions. So you need to have a larger radial force to pull it inside. That's why you see when a particle drops it from this particular red color plug over here. See, when it drops it from here, it completes one circle because it is getting that potential energy. When it drops it from here, you see, it goes only until this much and immediately falls from here. Okay, there are some calculations being made. Anyway, we'll come back to it later on. So this is what happens. Thus, okay, so greater the speed, greater the radial acceleration. A particle moving at higher speeds needs larger radial forces to change its direction. So you need to have a larger radial forces in order to make a particle to move around in a circle. But what you observe here is the radius is a constant, but still the particle is moving in a circular path. And also the angular velocity is a variable. What do you mean by angular velocity? We had already seen that angular velocity is nothing but v divided by r. Since the value of r is a constant, but the value of v is variable, and thus angular velocity is a constant, right? Okay, then let us look at the second possibility of a circular motion. Shown here is nothing but a string tied to a cork, and the string is made to go across in a cylinder, and you have put a weight over here. Okay, and then if you keep on increasing the weights, what happens is the tension in the string increases, and as a result of this, this circle, earlier it was whatever it was going in the form of a circle, now changes it into its spiral path, right? It forms a spiral path. The radius of the circle changes as the speed changes. As the weight increases, speed decreases, such that the ratio of v square by r remains a constant, right? And then, so radius also changes, v square also changes, so tension remains a constant. The radius of the circle is changing continuously, and the change in speed does not affect the centripetal force. In this case, it does not affect the centripetal force, while there exists a tangential acceleration. As the particle changes its speed over here, so it starts describing smaller and smaller circles. Ultimately, it reaches this point. So this happens. So then there's a tangential acceleration. So angular velocity changes here. Thus, what do you observe in both these two slides? In this slide also you observe that the angular velocity will be a variable. In the second slide also you observe that the angular velocity is a variable. It's changing over here. So in other words, when there is an angular velocity changes, then you call this as a non-uniform circular motion. But in case of a uniform circular motion, angular velocity does not change. Right. Now, if it is a non-uniform circular motion, how do you calculate the total force or net force acting on it? Now, as you see over here, see, in case of a uniform circular motion, there is only one acceleration acting here, which is centripetal acceleration. And there is a velocity of the particle, which remains a constant. This Vt is nothing but tangential velocity, which remains a constant as the particle keeps on going around in a circular motion. That's what it says, constant speed and constant angular velocity. So both of them do not change. But in case of a non-uniform circular motion, this tangential velocity keeps on changing, or there is a velocity along the tangent also. So this acceleration, okay, is called as a tangential acceleration. In addition to the centripetal acceleration, there's a change in velocity along this direction. So you get a tangential acceleration. Thus, as you observe, you have two accelerations. These are two vectors. Now, the sum of these two will now be inclined at some angle here, which is a total, right? So in case of a non-uniform circular motion, there's a changing speed. And what do you mean by changing speed? The speed of the particle along the circle changes, right? And there's a changing angular velocity. As this changes, the angular velocity also changes. So how do you calculate the angular velocity? By using this rule, right? By using a right hand grip rule. So what do you mean by grip rule? You say that, okay, when the particle is moving like this, then the acceleration is directed outwards from you, or it is towards me, right? So this is your acceleration. So therefore, due to the particle's changing direction, the angular velocity is now in this direction, right? So we have got the angular velocity. This angular velocity, okay, initially is smaller, then it becomes larger. In other words, it is like pulling my thumb outwards, right? So initially it is only so much. It is only so much. Say for example, if it is moving like this, it's only so much, and then it becomes larger and larger over here, right? So thus, okay, in case of a non-uniform circular motion, there are two accelerations, and the angular velocity is not going to be a constant. And sorry, just a minute. Okay, so now if I look at the net acceleration, how do I calculate the net acceleration? Our net total force acting over here is given by A total is equal to square root of A centripetal square plus A tangential square. What do we do here? We actually consider that these two vectors are perpendicular to each other, because this is along the tangent, this is along the center. So these two are perpendicular to each other, and thus if there are two vectors perpendicular to each other, resultant is given by sum of these two vectors, right? So therefore, we take this vector, which is A total should be equal to so much, and the total force acting on it is equal to M into A total. So this is how we calculate the total force in case of a non-uniform circular motion. So in the next class, we will see some of the problems in uniform circular motion and non-uniform circular motion both. So with this, let me end this class, and tomorrow let us see this, okay, with a new dimension on how to solve problems on circular motion. So far we have been looking only at horizontal circular motion, where I have not considered the gravity. Okay, maybe in a few classes we will also see circular motions with gravity. Thank you.